Quantum computing is the closest technology to commercialization that could revive Moore's law. Quantum computers operate using qubits, quantum bits. Unlike classical bits, qubits can maintain a superposition state, where they exist as both 0 and 1 simultaneously. Additionally, quantum entanglement allows different qubits to be strongly connected, sharing information instantaneously. These two properties enable quantum computers to perform extremely complex calculations simultaneously. Moore's law predicts the periodic doubling of transistor density in traditional silicon-based transistors. However, due to physical limitations, maintaining this growth rate is becoming increasingly difficult. Quantum computers, by leveraging qubits to perform many calculations in parallel, can achieve performance increases far beyond what traditional computers can accomplish by simply doubling their power. This presents a new paradigm that surpasses the performance improvements predicted by Moore's law. Let's take a closer look at how it works. Classical computers perform serial computation, meaning one operation must be completed before the next can begin. In contrast, quantum computers use the superposition of qubits to perform parallel computation. This allows multiple calculations to be executed simultaneously, with qubit states instantly shared through entanglement. Moore's law was designed to predict performance improvements in classical computers. However, with the limitations of serial computation, significant performance increases are no longer feasible. Quantum computers, through parallel computation, can dramatically enhance computational power, exceeding the performance gains Moore's law predicted. In other words, quantum computing offers a new level of computational ability that surpasses the limits Moore's law has set. Overcoming physical limitations. Traditional silicon-based transistors face physical limits, such as quantum tunneling, as their size decreases. Quantum computers, on the other hand, operate on an entirely different principle. Qubits function at the atomic or subatomic level, utilizing the laws of quantum mechanics at these small scales. This provides the potential to overcome the physical limitations faced by classical transistors. Moore's law has reached the limits of traditional silicon-based technology. Quantum computers, by performing calculations based on quantum mechanics rather than simply reducing transistor size, can overcome these physical limitations. This allows continued performance improvements as suggested by Moore's law and opens the door to a new dimension of computing. Quantum computers also excel at solving certain types of problems very efficiently. For example, problems like factorization, optimization, and molecular simulations are extremely time-consuming or even impossible for classical computers. Quantum computers can solve these problems quickly by utilizing parallel computation and quantum interference. Why this relates to Moore's law? Moore's law predicts the performance improvements of traditional classical computers, but in certain problem domains, classical computers face limitations. Quantum computers excel in solving these problems, meaning they can far exceed the computational performance gains Moore's law suggests in these specific areas. Thus, quantum computing opens new possibilities in areas Moore's law couldn't predict. Conclusion. Quantum computing, through the superposition and entanglement of qubits, overcomes the limitations faced by classical computers and has the potential to exceed the performance improvements suggested by Moore's law. This is realized through a surge in computational power, parallel processing, overcoming physical limits, and delivering exceptional performance on specific problems. Quantum computing will illuminate the future of semiconductor technology and play a crucial role in maintaining or even accelerating the continuity of Moore's law.
The first rule of channel is subscribe channel. Second rule of channel is click like. This channel will make you smart.